Yeah, my work is really more on kind of global scale fisheries and fisheries management than the Baltic specifically, but I've become involved with some of the Baltic fisheries work too over the years. This is actually a picture by an artist friend called Glyn Gorick, and the Technical University commissioned a book about all aspects of work in the university, and Brian McKenzie and I wrote a chapter, and we got Glyn to do some pictures for us. And what this is intended to represent is really, it's for the area around Denmark, the way in which there's been a fairly steady transition over the last 30 years or so from the typical cool water species that you see on this side of the picture towards increasing numbers of the ones that you see on the right, which are more warm water species. So, for example, there are more sole now relative to the numbers of plaice. Haven't completely replaced them, but there are just relatively more of these. And sea bass, red mullet. This is actually a bullet mackerel here, anchovies, and these are the typical cool water species, the herring, the sprat, the cod, saithe, mackerel on both sides. And then in the back you've got a swordfish looming, because there are a few of those that occur, particularly in warm summers in Danish waters. So it was to give an idea that there are these transitions going on at the moment. To begin with some large-scale context, I thought I would just show this picture partly to give an idea of scale and how the Baltic fits into the global picture of the aquatic food supply to humans. So we harvest around about 100 million tons of fish and aquaculture products per year. And you can see that actually the share of aquaculture has been going up very steadily. So by now, this only goes up to I think 2008, but now more than 50% of our fish food supply comes from aquaculture. The contribution of capture fisheries is fairly steady, around 60 million tons or so. And that trend is likely to continue. So when we think about fish as food, actually an increasing proportion of that does come from aquaculture. So if you think about 100 million tons there, the kinds of tonnages that you've seen already from some of the pictures that Torsten showed and that I will show, you can relate it to that 100 million tons. The Baltic produces really a not insignificant proportion of the global total. I think it's probably around 1% or so. The other picture that you've seen in a completely different form, which Marcus in fact showed, is some work that Igor Belkin and Ken Sherman did, and in fact what it shows is this is all the large marine ecosystems of the world. There's the Baltic right at the top in terms of warming during the period from 1982 to 2006. So the Baltic has actually been warming up at a rate over that period of 1.3 degrees per decade, which is incredibly fast. In fact, there's no way that kind of increasing rate can be maintained. And of course, it's not all due to global warming. It's also due to multi-decadal variability and other things. But really the point that I would like to make in relation to this is that when we ask the question, what can we expect as a consequence of warming, you can actually look back in time, because we have been experiencing warming of very rapid rates already. So we've already seen what one can expect as a result of very rapid rates of warming in this case. And some places, of course, are not warming at all. They're actually becoming cooler. But the Baltic is, and the North Sea are at the extreme of the range, or have been in the past. This only goes up to 2006. If you look at the very recent period, the last 8 to 10 years, if anything, I think we've probably been seeing cooling in this area. Certainly that is the case for the North Sea. And that may be because the balance of multi-decadal variability and global change has shifted. And of course, the other point is that when we think about climate, of course we don't only think about temperature. It's all these other things as well. So here they're grouped into the atmospheric or surface level phenomena, the wind, cloud cover, waves, sea level, and then you've got the properties of seawater that we can measure with a thermometer or some kind of chemical measurement, and then the dynamic characteristics, current, stratification, turbulence, and finally the larger scale climate indicators, the representations of some large-scale seasonal or longer-term process, the El Nino Southern Oscillation, the North Atlantic Oscillation, the Pacific Decadal Oscillation, which are all used to describe some aspects of the climate system. When we think about pressures on marine ecosystems, climate is actually the new kid on the block in many ways. Humans have been putting pressure on marine ecosystems for a very, very long time. And the reason for showing this picture here is just to put that into perspective. This was actually painted by Peter Bruegel the Elder in 1557, and it shows a large fish that's been eating smaller fish, and then a fisherman who's caught the large fish, and here's some other fishermen and all kinds of strange monsters out here. And at the time that this was painted in the middle of the 16th century, the human pressure on marine ecosystems was already so great that in order to supply the human demand for fish, people were exploring further and further afield. So one of the main reasons for the long sea voyages that people took to North America was to supply fish. And already by the early 1500s, there were quite big fisheries in Newfoundland on the Grand Banks, where Basque fishermen and fishermen from other countries were already exploiting fish for the European market. When I'm giving this talk, I sometimes show another picture, which is a map of the Grand Banks and George's Bank from 1776, in order to annoy my American colleagues, because the caption of the graph of this picture says the English claim to the fisheries of North America, the historic English claim to the fisheries of North America. And the point is that by 1770, or whenever it was that this picture was published, there had been European and English fishing interests in that area for over 200 years. So when they talked about historic interest, there really was a historic interest. And the other point about showing it is that already by then, a number of the species in that area, particularly things that were vulnerable in rivers and estuaries like sturgeon, had been depleted. So we think of depletion of fisheries as being a phenomenon that came along with industrial fishing, you know, the industrial trawlers that go along, hoover everything up. But in fact, people had been depleting fisheries, certainly in coastal areas, way back into the 16th, 15th century. The King of France commissioned a report on the fisheries of the French coast in 1723, because already by then people were worried about the way in which fisheries were being overexploited. And the kinds of questions that the King of France asked, or his ministers asked on his behalf, were: what effect does disturbing the seabed have on the production of food for fish? You know, benthic disturbance, what does that do? What does that do to fisheries? And a number of other issues like that. What's the best mesh size to use? Which are exactly the same issues that we're still grappling with and still not entirely able to answer. So anyway, these are the kinds of pressures that we've been putting on fishing, on marine ecosystems for a long time. Fishing, pollution, mechanical habitat destruction, introductions, and most recently climate change. And they all result in altered ecosystems of some kind. And so when we think about pristine ecosystems or trying to restore ecosystems, we really have to ask ourselves what point on this spectrum are we trying to restore to? And this brings in a phenomenon which has been called the shifting baselines phenomenon, where each new generation of scientists regards the state of the marine ecosystem when they began their careers as being close to the pristine state. And of course, every generation is wrong, because in fact things have been altered for a very much longer period than that. I think the other point that I would make, there was a discussion about using the word drivers or pressures or stressors and so on. I tend to use the word drivers myself, because when you think of stressors, then you're thinking of like I'm under stress, you know, I'm have domestic problems, and I'm beginning to develop a cold and so on. These are all things that stress me, and so they might make me more vulnerable to picking up some new virus that's going around at the moment. Well, it's a little bit like that with these pressures that humans put on marine ecosystems. And when we think about concepts like resilience, the ability to return to a particular state even though you've been pushed in some direction, then these can also be regarded as in some sense cumulative and having an effect on the resilience of the system. And there are ways in which you can begin to quantify that. In fisheries, for example, in particular, by looking at the age structure of the populations that you begin with and what you're left with after you've been exploiting them. Okay, moving on to what climate actually does. The organization that is responsible for management of the Northeast Atlantic is a thing called OSPAR, the Oslo and Paris Commission, and they wanted to have advice from ICES about the state of marine ecosystems and whether there were detectable climate change effects. This is a report that was produced then in 2008 on the effect of climate change on distribution and abundance of marine species in the OSPAR area. And so they said, can you tell us whether climate is already having a detectable effect, and how strong is the attribution? How confident can we be that it is actually climate that's doing this? So we did a big survey of all the information that we could have, all the time series that we could find on changes in distribution of species, abundance, and the seasonality, the seasonal timing, phenology, for, in the end, 100 species of fish, 88 of benthos, 83 of plankton, 20 of seabirds, and there were in fact a few marine mammals in there as well. And what we found was that yes, climate is an important factor in the changes in distribution, abundance and seasonality in the Northeast Atlantic. So the answer was yes, we can definitely detect the signal of climate on these things in relation to species in the OSPAR area. The attribution to man-made climate change is much more difficult because we saw the warming here, again the same thing, very, very rapid rates of warming, rates of over a degree per decade over this period. And that's not entirely due to anthropogenic climate change, that's also due to multi-decadal variability and natural variability and so on. So to say that it's specifically due to that part of the warming signal is very difficult, but it is entirely consistent with what we would expect if warming takes place.
Excuse me, why isn't the years between 78 and 82 included? It says minus 1970. Sorry,
that's the way that the time period is defined. You're looking at a difference, a delta sea surface temperature between that 5-year average as the beginning period and that 5-year average as the end. And when I said per decade, in fact that isn't a decade, that's more than a decade. That's 25 years. But nevertheless, if you think about expected rates of global warming as being in the ballpark of 0.2 of a degree per decade, that's very, very much faster than the global mean for And in fact, over the period, if you look at the global mean temperature rise over that period, it's probably closer to 0.1, 0.2 degrees per decade, and this is very much faster than that. This is up around 0.3 or 0.4. So we've been experiencing locally rates of warming that are 3 times faster than the global climate change signal. And that means, of course, that in terms of the effects, if you're going to go anywhere on Earth to find out what the effect of warming is, come here, because this is where there's already been very rapid warming. And of course, we do have better data for this part of the world than almost anywhere else. So we are perfectly placed to detect things if they're happening. What else? Well, the other thing that has been happening is that species richness of fish in the North Sea and in the Bay of Biscay has been increasing pretty rapidly. In this case, the period in question was, I think again that's a 30-year period over about the same, oh yeah, here we are, 1980 to 2010, of course. So what you see here is simply the number of species in different areas, and as a function of year and as a function of temperature. And it's pretty clear that what's been happening is that the number of species in the North Sea has been going up. And the reason for that is because a lot of new species, like the ones that I showed you in the picture, have been coming in, or warm water species have been increasing in abundance. But they haven't pushed out the old familiar cold water species. They have added to the richness of the area. So biodiversity has been increasing in the North Sea. Well, the simple view is that more biodiversity is good, and therefore maybe this is a good thing, that we've now got greater species richness. Interesting question. Is it or is it not? And another question would be, but is this just a transient effect, so that it takes time before the cold water species realize that the game is up and they disappear off to wherever? Well, there's some interesting work being done on archaeological remains, looking at kitchen middens from the Stone Age, particularly in Denmark, and analyzing the bones that Stone Age people were throwing out 4,000 or 5,000 years ago. And at that time, you had a period called the Mid-Atlantic Warm Period, when the temperature was higher than it has been. It was about the same as it is now. In other words, warmer than the recent average. And at that time, you also got these warm water species in their diet, but you had the cod and plaice and other things that we regard as cold water species also there. So it looks as though the transient effects, if they occur, are actually very, very long. It may take a very long time before the cooler water species get pushed out of areas like the North Sea and the Baltic. And in the meantime, we've got a mix of the warmer water species and the cooler water species. Now, one of the other things that people immediately think about when they think about the effects of warming and distribution shifts is that, maybe I'll just leap out of order here slightly. Yeah. This is a headline from Jyllands-Posten, where you had the Prime Minister at the time up in the top right-hand corner, but the headline was, warm water species in Danish waters. So it was actually made the front page of one of the national newspapers in Denmark, which was really interesting because the date of that was January 2004, and this picture was actually published in the Italian Journal of Zoology in 1998. So it took 6 years for the news to reach from the Italian Journal of Zoology to the front page of Jyllands-Posten. But anyway, I mean, people were interested enough that the journalists felt that it would, and these stories do quite often make big news. People are interested. Distributions change, productivity changes, some species decline and others become more abundant. Well, and this shows a particular pair of species, a particular pair of dories that were first found off Portugal in 1963, and by 1993 they'd been found all the way up to the west of Ireland. So the rate of movement was really very, rapid. And here's some of the other species, new species, anchovy there. Now, let me just go back to where I was. The anchovy is really interesting because when people think about stories like that, it's pretty obvious that the dories, they actually migrated. I mean, they weren't there at all before, and then they started to appear. So, individual fish actually started to move further north. But with the anchovy in the North Sea, we know that the population of anchovy in the North Sea has increased enormously in the last 30 years. The question is, are those anchovies that came from the Bay of Biscay, or is it a relict population? There were a few anchovies always in the North Sea. Is it just that that population has increased? And the answer is, it's the latter. It's actually a relict small population that has now become much more abundant. Now, in the context of the Baltic, I think the interesting issue there is one that we've already talked about briefly. When people now, for example, are detecting a few cod in around Finland, is that because fish have actually moved from further south, or is it because there have always been a few cod in that area and they're now becoming more abundant? And those sorts of issues, of course, are absolutely critical when you want to try to model the processes that are involved in changes in distribution and abundance. Yeah.
So that means that for some species, for example, that we are worried about the distribution range are going up. So that can be that these species are just returning to the previous places where they were.
Yeah.
They have to. They went south because of the colder periods, and now they are getting up again.
If you look at over geological periods of time, then the Baltic didn't exist 10,000 years ago, so everything is a newcomer on a geological scale as far as the Baltic is concerned. I think myself that we can't exclude any of the possibilities. It's possible that some things are relic species. In other cases, they've definitely moved into the area. For example, recently people have found blue mussels on Svalbard. They weren't there before. And the only place they can come from is the nearest population of blue mussels, which is Norway. So somehow a few individuals or a few planktonic individuals have made that huge leap. But thinking about changes in distribution as involving something swimming is definitely a mistake. If you think about forests, then you wouldn't make that mistake. I mean, forests don't pull up their roots and walk north. So of course we know that there you've got to establish the population by wind-blown seeds or whatever. And in the sea, we shouldn't think about shifts in distribution as involving something actually swimming. It may not be that. It may be that it's a relic population, or it may be a planktonic stage that was carried. So where are we now? A long history of changes in marine systems. Pressures accumulate and interact, and there is no pristine state for conservation. In terrestrial conservation, like the built environment architecture, people are often trying to preserve old buildings, and of course that's a nice thing to do. But you find that there are certain fixations that people have about what is traditional and what should be there. In England, our royal family, we're blessed with Prince Charles, who's very interested in architecture, and he's been a curse on the architecture profession in the UK for a long time because he hates anything that. And somebody tried to work out, what it was that he hated, or rather when he started hating, and it turned out it was about 1827 that everything since then he thinks is horribly modern. And so he's actually been building villages that resemble what people were building in the early 19th century. So, there is no pristine state. I mean, why he picked that period, I don't know, but anyway. Okay, I think I've talked about this. Change can be very rapid in the sea. These changes are very, very fast indeed. And of course, because it involves currents and movements of water masses, that's quite understandable. There can be very big productivity changes and declines and other things becoming abundant. Okay, moving to the Baltic. We've already seen this picture. I think I've perhaps updated it a little bit. And the Baltic, in many ways, is a very simple system. from a fisheries point of view, there are really just these three main species. Now, here we've got the spawning stock biomasses, so we're dealing here in 1, 2, 3 million tons of biomass for these three species. And I haven't got the catch figures here, but they're of the order of hundreds of thousands of tons up to sometimes 1 million tons for these three species. And remember back to the first picture that I showed where the global fish food production was 100 million tons. So the Baltic is big. It's a big player on a global scale. And what you see here are, particularly for for sprat, a big fluctuation there from 500,000 tons up to nearly 2 million tons in the spawning biomass of sprat over quite a short time period during the 1990s. For cod, you've got this big biomass period during the late 1970s, 1980s, and then since then a decline. If you'd gone back much further in time, I think in the 1920s and 30s, then there would have been probably a couple of flatfish species that would have featured on here as well, plaice and flounder. But they're very small now, and I don't think anybody really quite knows why it is. I don't know whether you know the reasons for the decline in the two flatfish species, but as far as I know, I mean, people have inferred that there are changes in the benthic production and so on, but it's not clear why those have disappeared. I also put this on because suddenly there's this blonk downwards at the end in the cod biomass, and the reason for that is very simply that there are two components that are assessed to produce this figure. One is the Baltic proper, the area east of Bornholm, which is where most of the Baltic cod come from. And that eastern component is simply not included here because we don't know what it is. We don't know what the biomass of eastern Baltic cod is at the moment, and I'll be talking quite a lot more about that. So that's not a real drop. That's just because we actually don't know what the number is for eastern Baltic cod.
But sorry, how was it included beforehand then?
Good question. I'll be dealing with that quite a lot more, so I will answer it, but I probably answer it straight away. No, I'll get into it pretty quickly though. This picture, again, we had some similar pictures earlier on showing the distribution of these three species earlier on. This is actually for 2012, the distribution of herring, sprat and cod in the various surveys that are used to produce the ICEDA's advice. So this comes from the advice from May 2013. These blue areas here weren't sampled. And these two, I think, are from acoustic surveys, and that one's from bottom trawl surveys. So in this case, the bottom trawl survey did actually cover the whole area of the Baltic, but cod were almost entirely confined to this southern area south of 56 degrees 30 minutes. Very few cod caught north of that line. For herring and sprat, the distribution was a bit more widespread, particularly for sprat. One of the points that I would just make in passing in relation to this is, of course, when you're thinking about the interactions, the biological interactions between these three species, a precondition for a biological interaction to happen pretty much is that they've got to be in the same place at the same time. If they're not, then saying that cod predate on sprat or whatever is, you have to be careful because they actually do have to be physically co-located for a lot of these biological interactions. Not all of them, but for them to be happening. So one of the questions that I'll be coming back to is why are the cod all in the southern part of the area and not further north? Now, with cod, the Baltic cod is really well studied. There are many aspects of its biology which are probably better understood than any other fish stock in the world. There really has been a lot of work. And the picture that has come out from that is a very interesting one, because if you look at the drivers of change in cod biomass in the Baltic Sea, there are actually 4 components that have been listed and described. The first one very clearly is fishing. And the fishing pressure on the Baltic cod has been very high, mostly too high for a very long time. So this green here represents a fairly low level of fishing, but then it increased. It was very high in the 60s and 70s, has come down a bit, but off and on has been really high, probably too high over much of the last century. Seals used to be very abundant in the Baltic, and they do predate on cod, and so there is some evidence, although it's not particularly strong, that seals had a negative effect on the biomass of cod in the Baltic, at least until the 1930s or so. After that, the seal population declined, and the idea is that they really don't play very much part in the fluctuations that have been observed in the cod biomass. The story for seals is really pretty uncertain. I think there are quite a few people who would say that seals never really had a big impact on cod dynamics, but I don't think we really know. This, though, if you remember, again, some of the earlier pictures could be regarded as a top-down, well, fishing and seals could both be regarded as top-down controls on what the cod biomass is doing. Nutrients is a very interesting one, because here you can see that there's a period in the mid-1950s where the thing turns green. And here there is actually fairly good evidence that nutrients do play quite a big part in the cod biomass. This could be regarded as a bottom-up effect. In other words, how much primary production, how much food production is there. And it does seem that with the addition of nutrients from agricultural runoff and so on, this had an effect on the production of fish food, probably not for the adult fish, but probably for the early life stages, which had a positive effect on the biomass of cod. And the balance of that has shifted. Maybe you can get too much of a good thing, and once you start to get into eutrophication, then you get problems with oxygen deficits and all the rest of it. So it may be that there's some optimal intermediate level of nutrient input as far as the cod are concerned. And then with climate, the story here relates to not temperature effects but salinity effects, because there is no other major area where cod exists, with the possible exception of the Gulf of St. Lawrence, where people even bother to look at salinity data, because cod is perfectly happy in salinities, well, the adults are perfectly happy in salinities down to, I don't know, 5 or 6 and up to whatever. And so for most areas where they occur, salinity is not an issue, but in the Baltic it is. And the magic figure there is 11 salinity units. And that's not because salinities lower than that are necessarily a bad thing for adult cod, but it's because there's a very specific period during their life history, during fertilization and early life, when the salinity is critical. And it's critical for a number of reasons. One is that the sperm, cod sperm, actually become inactive if the salinity drops below about 11. The second is that the eggs will float in salinities of more than 11 at the sorts of temperatures that we experience here. But below that, they sink in the water column. And so since the spawning is mainly in deep areas and there are anoxic layers at the bottom, if the eggs sink, then they fall into the anoxic layers and they die. And there are also effects on the larvae as well. So there you have a case where you can do an experiment in a density gradient, or activating sperm in the laboratory, or stripping sperm in the laboratory, And from that kind of laboratory experiment, you can make an inference about the mechanisms that affect the dynamics of the whole cod population in the Baltic. So it's quite a critical bottleneck in the life history, if you like. And it's believed to be a major factor in variability in recruitment. So what you see here is the time when there were major inflows that increase the salinity in the deep basins where the spawning occurs and are thought to be beneficial for recruitment. And that's a very nice story of how scientists did great work looking at processes and relating from small-scale laboratory-type studies to the big scale and making predictions about what the consequences of salinity change were going to be for the population. Yeah?
Yeah, I just have a short question. Maybe that might be a bit picky, but why did they name it climate then, but not salinity?
Well, that's a very good question. This is really, it shouldn't be called climate, it should be called environmental drivers.
Yeah, because
Yeah.
actually the time spans that
You're absolutely right, yeah. No, this is really an environmental driver, not necessarily climate at all. I mean, to be climate, it would have to be related to a change in the wind field that alters the inflows, or precipitation, or the other things that might be climate related. And in fact, when we look into the future, of course, and the future of the salinity environment in the Baltic, then we are talking about the climate link. But strictly speaking, you're absolutely right. This should just be environmental influences, or even salinity, if you like, in this particular case. But as I'll go on to talk about, what we were certain about a few years ago, or pretty certain about, we no longer are. So, like almost everything in biology, you come up with a really good story, and then shortly afterwards you find, well, that's not quite the whole story. It's not wrong, but it's not complete. And that's unfortunately what seems to be the case with the cod story in the Baltic. If you want to read up on that last section of the talk, then this is a very good paper by Margaret Eero, and it includes that picture that shows the four major drivers. Are we supposed to be having a break about now? Let me just check what the next picture is. Yeah, this is probably quite a good place for a break. Would you say? Okay. It's a work that led by Martin Lindegren, who Torsten mentioned earlier on looking at the risks from a combination of climate and fishing, the risks to cod in the Baltic, the risks that it will actually disappear. And here again, salinity is being used as the metric of climate. And we heard earlier on about projections of what salinity change might be in the Baltic. And the point is that of course, if you fish with a very high level of fishing, then you can cause the Baltic cod to go extinct. You could actually wipe them all out. And if the salinity drops by a very large amount, then this requirement for salinity is higher than 11 during the spawning period would no longer be met, and again they would go extinct. But the two pressures interact, so depending on how much the salinity might drop, you actually have more or less scope for fishing heavily, and a combination of the two will cause extinction at some intermediate levels. So that's quite an interesting a piece of information to give to fisheries managers, that there are interactions between the different pressures on the fish stocks. This was produced from a rather nice regression-based model. So it is based on actual data that for what the dynamics have been in the past. And it is something that is now embedded in the thinking about the likely future of cod in the Baltic. Well, this I said that I would talk a bit more about the cod in what's called subdivisions 25 to 32, which is the area east and north of Bornholm, because as you can see, this was still is a fairly major part of the total cod biomass in the Baltic. So this is the report on cod in those two subdivisions that came out from ICES in 2013. And they produce a very nice summary which is intended for fishermen, the general public. You can find it very easily on the ICES website. And it's a simple, it's a series of graphs presenting information about the changes in catches. So you see up to 400,000 tons there in the mid-1980s. The recruitment, the number of young fish, the number of 2-year-olds coming into the fishery, the fishing mortality, and the spawning stock biomass. If we look at these two, what you see is that over this period, the last few years, fishing mortality has been coming down very quickly. And we think that the fishing mortality was really too high. That's the metric called the fishing mortality that's needed for maximum sustainable yield. So anything above about 0.45 is too high to produce maximum yield. And it's been dropping very quickly and was then believed to be below that magic level. And the spawning biomass has been going up over the last few years in a very satisfactory way because there were a series of quite good recruitments, better than there had been for about 20 years or so. So the situation looked fairly rosy, and they said the spawning stock biomass has increased in recent years, now estimated to have been above the precautionary level since 2008. Fishing mortality has declined and is now estimated to be below FMSY. And the abundance of the recruit year classes is good. So, good news, great. One of the most successful stock recoveries in recent times, fishing mortality declined, biomass increased, recruitment increased. Why? I mean, one of the things was supposed to be that increasing salinities were good for recruitment. So it's not quite clear why it's increased, but let's be happy anyway. And these positive developments were partly ascribed to effective management. So everyone patted themselves on the back. And this paper, which just came out just over a month ago, different story. Eastern Baltic cod in distress. Biological changes and challenges for stock assessment. The Eastern Baltic cod is one of the best studied cod stocks in the whole world. And this year, ICES have classified it as among the stocks for which we are data poor. And they can't do an assessment. They don't know what the hell is happening because they say that the numbers just don't make sense. So how can it be that one of the best studied stocks in the world is regarded as data poor? If this is data poor, then we don't have any hope for anywhere else. And the reasons, there are many reasons for this. But the situation really is very difficult indeed. So to go over what has happened, this shows the change in biomass of juvenile fish for the Eastern Baltic cod, less than 30 centimeters, from the groundfish surveys in the first and fourth quarters of the year, covering the entire central Baltic Sea. So the number of small fish, of juveniles, has been increasing very nicely. But the number of bigger fish, greater than 38 centimeters, has been going down rather sharply. And that doesn't really make terribly good sense. Why is the Eastern Baltic cod suddenly in difficulty? Well, one of the things that we've already seen is that the range is restricted. It's mainly found in the southern part of its previous range. And the reasons for that are not really clear. It could be that the conditions further north are not good, that there is an oxygen deficit that they find unacceptable. Or it could be that in fact the stock does consist of subpopulations, and that the reason that there aren't any or very few cod in the northern area is because that's a substock which is actually at a very low level and hasn't recovered. It could be something to do with homing, that the present population was all spawned in the southern areas and that's where they're remaining. We really don't know why it is that the range is restricted, but that seems to be the case. The second thing is that the condition is poor. What we mean by condition is the weight of the fish, how fat they are in relation to their length. And that's, I'll show a graph in a minute, that's usually represented by the exponent of a cubic function relating weight and length. But the condition is poor. And the third thing is that there are a lot of parasites. And of course, one of the reasons that the condition is poor may be because of parasites. So here are the figures for the condition. So the average condition, which is this thing called Fulton's K, basically that means that if you have a Fulton's K of 1, that means that you can cube the length, and that gives you a length-weight relationship. A Fulton's K of more than 1 means that you more than cube the length, so they're really fat fish. And if they have an exponent that's less than that, condition index less than that, then it means that they're skinny. And so you can see that their condition has been declining over the last 10, 15 years or so. And this is showing the proportion of fish with a Fulton's K of less than 0.8, which is, I think, a fairly critical value. If they have a very poor body fat, then of course they have less energy to put into reproduction. But nevertheless, we've got this good recruitment going on at the moment. So it doesn't. There are lots of things here that don't quite hang together. Anyway, that's the condition. This is the parasite story. There are lots of fish which are infected with a liver parasite. And this shows the numbers of fish greater and less than 50 centimeters with this parasite. So you can see very high numbers here. These are data from the Bornholm and Dansk basins. Again, the reason why the parasite has become more abundant is not clear, and you often get a kind of chicken and egg situation where they're in poor condition because they've got parasites, but they may have got the parasites because they're in poor condition, so we don't know. What we do know is that the intermediate host for this parasite and another one is grey seals, and the grey seal population is higher now than it has been, so maybe that's something to do with it. But in any case, that may be causing increased mortality of the older cod, and maybe part of the reason for the decline in the abundance. In other words, there is now higher mortality than there was in the past. The third big issue, which is particularly embarrassing, I think, is that the age reading is unreliable. Well, here you have a stock that has got people from all around the Baltic studying it, working on it for many years. How can the age reading be unreliable? It's just a very, very basic thing that is fundamental to carrying out stock assessments. You look at the age structure, and from the age structure you can say what the mortality rates are, what the recruitment is, and what the growth is. In order to be able to get a growth rate, you have to have some time scale to work on, and with fish that is age reading. The age reading is done by looking at the otoliths, counting the number of rings. And this is an issue which is actually quite prevalent. This is not the only stock for which we are now realizing that the age reading is unreliable. And it's partly to do with the sociology of science and scientists, if you like. I actually did a couple of papers when I was about your age about the reliability of age reading and the problems that you would get into if the age reading was unreliable. But the actual job of age reading is time consuming, and you sit there at a microscope and you have 300 otoliths to read by next Wednesday or whatever, and it's a boring job, and it's not one that you want to do for the rest of your life, and you don't make a good scientific career out of it. You know, it doesn't win you brownie points reading otoliths. You know, you hire people who read otoliths, and some of them become very expert, very good at it. But how do we know that they're expert? How do we know that they're really reliable? And the answer is, we don't. We kind of assume that they are. The problem is that if, as with the Baltic cod, you have people in different countries, different laboratories who are all reading their own otoliths, then one day somebody thinks, oh, let's put them all together and see how they compare. And you discover that the otolith readers in the different laboratories have got completely different ideas about ages. They don't compare between each other. And internally, they're not consistent either. And so it's one of these things where quality control is really important, but it's almost entirely lacking. There is almost no international quality control. And this is not a phenomenon which is restricted to age reading. It's also true for many other things that we take for granted. I don't know what the situation is like now, but a few years ago, there was perceived to be a very big problem with measurements of salinity, nutrients, and all kinds of chemistry in the Baltic and other areas. And so international quality control workshops were set up to try to do international quality control. But at the time, I was working at ICES, and my colleague Harry Dooley there, who was in charge of the statistics department, claimed, and I think he was right, that he could tell which chemist had been on which cruise by looking at the results from their marine chemistry observations, because they used different standards, there was different variability, and they had certain characteristics which allowed you to identify the individual who'd made the measurement. Well, that's not a very good thing if you're having to then base projections on this kind of stuff. So this is a very, very serious issue, and it's one that people are quite aware of now, but it's actually not easy to do anything about it. And there may also be problems with, because the fish are in poor condition now, the actual otolith structures are changing. The other thing that we know about Baltic cod is that the seasonality is changing. There's far more autumn spawning now than there used to be, and that may also cause differences in the structure of the otoliths. So recent biological changes may also make it more difficult to do this age reading. If you haven't got good age reading data, then you have to fall back on other methods, length-based methods and so on. And so that is part of the reason why ICES said that this was a data-poor stock, because the assessment scientists lost faith in the age reading, and so they said, we don't know what the hell's happening. We're lost. So that's the situation, I think, as it still is now. Right. Moving on. Some of this we have already touched on. I think Torsten dealt with some of the same field. There is no question that climate change is shifting the goalposts in terms of fisheries management. When I said that, when I showed you the picture of the interaction between salinity and fishing mortality in terms of the risk of extinction of Baltic cod, you could call that shifting the goalposts. You know, the goalposts used to be that the Baltic had a certain salinity and inflows happened at a certain frequency. If you start fiddling around with those things, then of course you're going to alter the productivity, the biomasses that are acceptable, and the reference levels that are used for fisheries management. And those, and if you alter the species composition, again, this is shifting the goalposts. One of the things that you realize if you work in policy advice in you know, working as an advisor to people like the EU Fisheries Commission, is that they hate scientists to come along and say, what I told you last year is no longer quite true because the goalposts have shifted. They love to have, you know, the common fisheries policy where everything is written down by the lawyers in legal language, and you know, that's it, fixed forever. I don't know whether you saw, but there was an article in the paper, maybe just in the English newspapers last week, that a shoal of bluefin tuna has been detected off the southwest of England. Well, they shouldn't be there. You know, you don't normally get bluefin tuna off Cornwall, but there they were. I think 500 tons or something, somebody estimated, bluefin tuna. And of course, they're enormously valuable. And the local fishing industry would love to go out and catch them and sell them to the Japanese. But they're not allowed to because they don't have a quota for bluefin tuna. The bluefin tuna quota is based on historic allocations, and that was set in the 1970s, based on catches over the period from 1965 to 1975 or something like that. And so bluefin tuna aren't supposed to be there. They're supposed to be in the Bay of Biscay and the Mediterranean and so on. And so the people who have the right to catch those fish are the Italians, the Spaniards, the Portuguese, the French, but not the British. And unfortunately, nobody told the bluefin tuna about this, and so bluefin tuna are now found all the way up to Greenland sometimes. But the legal documents about how fisheries are to be managed are based on a historical allocation which doesn't bear a resemblance to present reality. And those are the kinds of issues that arise when you put scientific advice together with management policy. You tend to get things set in concrete where people try to do things the way they've always done them, and in the meantime the goalposts have shifted. I think Torsten mentioned the Marine Strategy Framework Directive, and that's a very interesting piece of EU legislation about how to manage the marine environment, because what it says is what we want is healthy and productive marine ecosystems. And everybody can agree that that's a good objective. And then below that, it has some sub-objectives that say we want levels of noise in the marine ecosystem that don't cause disturbance to the species there. We want healthy, productive fish stocks. We want no marine litter. We want, all these kind of general objectives. And then underneath that, there are 11 descriptors of good environmental status, and that's when you start to get into the detail about what all this actually means in operational and concrete terms. But those descriptors, although they're written down in some detail, they can be changed. In a sense, they are the best practice, the best scientific advice that we can have at the moment. So you don't have this setting of things in concrete forever. You can actually change things. And the emphasis is very much on the process of achieving rather than exactly what the goal, or rather exactly what the operational goal for the thing should be. I think I've already talked about there is no fixed healthy ecosystem state. These things do change over time. I've also mentioned this, whether more biodiversity is always a good thing. I mean, broadly speaking, the Baltic is much less biodiverse than the North Sea because it's much more recent. I mean, it's a very new sea compared with the North Sea. We can't expect the same levels of biodiversity in every area. There are going to be quite big differences, but the question of whether more biodiversity is always a good thing is of course quite important, because there are biodiversity targets in the Marine Strategy Framework Directive, for example. But if you think about policy on things like peat bogs, I mean, peat bogs are low biodiversity areas, and we want to preserve peat bogs, so we don't want them to become more diverse. If you put fertilizer on peat bogs, then they become more biodiverse, but that's a bad thing. So more biodiversity isn't always a good thing. How far will acidification and hypoxia alter marine ecosystem states and productivity? Well, that's a question that I think is very critical for the Baltic in particular. And then we can also ask about such things as carbon sequestration. So there are quite a few big issues where the Baltic is a particularly interesting area because it is at the extremes, and these things are coming into existence quicker than they perhaps are in other parts of the world. In case anyone wants to look at that paper, I thought I had the reference here. There are actually 2 or 3 papers, but this one in PNAS is the main one that you could have a look at. So that was an attempt to make a projection for fisheries. But why do we need better projections? Well, managers are interested, and it does have an influence on the way that policy is shaped. So there are people who will use this information, but then you have to ask yourself what time and space scales are needed. And a lot of the fisheries management is conducted on a year-to-year basis. And that's a good thing, because it's very difficult to make projections over long periods of time. And if you waited until you understood a system well enough to model it, you'd be waiting a very long time. And there has to be some attempt to keep, for example, fishing mortality at a reasonable level. And so it is necessary to work by constantly updating fairly short-term projections. So fisheries management is largely based on 1 year ahead projections. The scales are determined by a number of things, and I can't really go into that, but they tend to be on fairly large areas, because it's too expensive to try and do research on very small areas. Even if we knew that the Baltic cod consisted of, I don't know, 10 different subpopulations, would we be able to afford to monitor those individually? Maybe, maybe not. Are the relevant projections available and understood? Well, that's a matter of quite a lot of concern, because it's not easy to convey complex models. How much are the users willing to pay for them? In this part of the world, quite a lot. I mean, there is quite reasonable funding compared with other parts. How reliable do the projections have to be? In some cases, even an unreliable projection is better than no projection at all. In other cases, people have questioned whether we should be putting forward projections because maybe they're worse than useless. It's a tricky issue to match the quality of projections to what actually will be helpful. I want to just end up by talking a bit about adaptation, because in many ways that's the topic that immediately comes up when you start to talk about climate change. Mitigation means actually taking actions that will reduce greenhouse gas emissions. Adaptation means accepting that there will be future changes and thinking about how you can do something that will minimize their impact. You could say that because it's very difficult to make reliable projections, there's nothing that we can really advise on, but that would be quite wrong. If you think back to the first slides that I showed about all the different pressures that there are on marine ecosystems, overfishing, pollution, eutrophication, habitat alteration, those are old issues that have been around for a very long time. We know that if we could reduce fishing mortality, as is happening now, then in many ways the fishing industry will be better off. They'll have better catch rates, they'll have bigger catches, and the actual fish ecosystem will consist of a wider range of ages, and we think that will give it increased resilience. Now, what's that got to do with climate change? Well, it does have to do with climate change, because I think that there's a very clear case for saying that if you have a more resilient ecosystem, then it will be more resilient to future climate change as well. And therefore, dealing with the old problems of habitat alteration, overfishing, pollution and so on, will actually also help you with dealing with climate change, because it will leave you with a more resilient system. So maintaining ecosystems in a state that is resilient to change doesn't involve any new measures. It just involves actually putting into force the ideas that we've had about better management of the old pressures. These are from the IPCC report. The IPCC, of course, is thinking about people. So enabling occupational flexibility. If you say to fishermen, you're going to have to fish less, then they might come back and say, well, okay, what else do we do with our time? In many parts of the world, fishermen also have other occupations that they take part in. And very often governments try to stop that. They say, no, you're either a fisherman or you're a farmer. You can't be both. It makes it too complicated with our taxation or statistics or whatever. Well, actually, occupational flexibility is a very useful thing to preserve, because it does mean that if you want to reduce pressures in one part of the system, then there are alternatives. Developing early warnings for the system for extreme events, that's something that I think people are becoming increasingly aware of, that change is not just change in the mean. Very often it's change in the frequency of extreme events, and very often it's those extreme events that cause the big problems. In relation to the Eastern Baltic cod at the moment, one might ask, is what we're seeing now, are the problems where the stock appears to be in a bad shape, caused by some extreme event? Is it because there's been no reoxygenation of the deep basins for a while? Probably not, but there may be other things that we really need to be able to develop early warnings for. And the IPCC has a confidence-based system, so they gave medium confidence to these key adaptations. Well, who does the adaptation? If you think about marine ecosystems, we could all stand on the beach this afternoon and shout, "You're going to have to adapt!" But the marine ecosystem is not going to pay a lot of attention to that. So yes, of course, the marine ecosystem will adapt, but not because we've thought about it and written a report. That will happen anyway. There will be changes in behavior, distribution, and phenology. There will be acclimatization. We know that populations are capable of acclimatization up to a point. Possibly shifts in balanced polymorphisms. For example, with cod, there are different hemoglobin types. Populations often have a mixture of different hemoglobins, depending on the temperature and the depth distribution and so on. One or other of those hemoglobin alleles may be more favorable. And so if you get a shift in temperature, then the balance of the polymorphisms in a population can change. Those things probably all happen. Genetic adaptation, of course, is on a different time scale. There we're talking about selection of new alleles, and that probably takes place only very slowly. There's fascinating work going on at the moment on epigenetic effects, which people are only just becoming aware of, that not all inheritance is via DNA, but that's really very early days, and it probably won't help with adaptation to climate change. So biological populations will adapt. It's just that there's not very much that we can do to help that happening. In capture fisheries, in aquaculture, it's a different story. In aquaculture, of course, it's people, it's the fish farmers who decide what strains they're going to cultivate, how they're going to feed them, and there's lots of adaptations that are possible there. For example, I was at a meeting fairly recently in the Cook Islands in the Pacific, and there they produce pearls, black pearls, in the lagoons. And they're very worried about extreme events, about sudden heating events, because that would kill off the oysters. So they want advance warning of heating events, because if they get the advance warning, then they can actually lower the cages where the oysters are to deeper water where it's cooler. So, a very simple adaptation that they can put into place to help their oysters to survive. People have actually talked, in the case of the Baltic, of trying to overcome reductions in salinity by helping the eggs and larvae through that quite short period during and after spawning, and perhaps having rearing facilities that just reared them through that short period when they need slightly higher salinities. But it's people who mostly do the adaptation. And the IPCC divides what they do into two categories: autonomous, which means you don't have to tell them, they'll do it anyway, and planned, where you usually through the governments or local authorities actually try to put into place some kind of adaptation strategy. Now, in the fishing industry, if you think about the pictures that we've seen of fluctuations in biomass and catches and species, in most parts of the world, the fishing industry are used to very big changes in what's available to catch from year to year. There's a wonderful quote by a Norwegian clergyman in the 16th century, where he's talking about the herring coming ashore in different parts of the Norwegian coast from one year to another, so that in some years the herring are entirely taken away and they appear somewhere else. And he said this is the will of God for the ingratitude of man. So if you don't show proper gratitude to God for providing herring, then he'll send the herring somewhere else. Well, now we're much less certain that we understand why it is that herring move from place to place, but we do know where they go. But this means that the fishing industry have always been used to adapting, and they do that all the time. In the North Sea, for the last few years, the Scottish fleet have been very largely basing their fisheries on squid. Well, a few years ago, they never caught squid there at all, but now there are plenty of squid there. They know there's a market, they go out and catch them. So that's autonomous adaptation. Planned adaptation is the kind of things that people do after they've read the IPCC report. So if we think about the timescales and the decisions, this is actually from a colleague in Hobart in Tasmania who worked with salmon farmers, and he scaled the whole thing from 7 to 10 day decision making to decades and centuries. Now, this is not climate change. 7 to 10 days has got nothing to do with climate. It's not until you get to decades to centuries that you can really talk about climate. But of course, to fishermen, for one thing, they're not interested in decades to centuries. They're much more worried about what's going to happen next week. But the other thing is that, of course, there is a continuum. And so if you're trying to talk to people about the need to adapt to climate change, it's often very good to start off by talking about weather forecasting and whether better weather forecasting will help them in their activities. In the case of fish farming, it very often will. In the case of the salmon farms in Tasmania, for example, there was a project in which they tried to produce seasonal temperature forecasts, because if the temperature is high, then the incidence of disease to the salmon is going to be higher, and they can plan for treatment regimes to control that. And the second thing is that the salmon grow faster if it's warmer, and they've got to plan when they're going to sell them. So they alert their sellers to tell the restaurants that certain quantities of salmon will be ready by certain dates. They make contracts, and if you can tell them what the temperature is going to be, it helps them to be much more precise and get a better price for their fish. So what to wear, aerators, feed cycles, these are all things that they'd be interested in just from very short-term weather forecasts. Of course, in their part of the world, cyclones and so on. And then here, stocking and harvesting, buying quota, how much labor are they going to need, what weeks in the summer are they going to need extra labor to harvest the buying equipment, and so on. So you go all the way through. Australia is very interesting because it is being impacted quite a lot by climate change already. People like fish farmers and agriculturalists and wine growers are very aware of this and are already in full swing with all this kind of planning. Their government is, as you probably know, in climate denial and says it's not happening. And there's this complete disconnect between what's actually happening on the ground and the political discourse. And the political discourse is a bit like, clerics arguing about how many angels can dance on the head of a pin. It's got nothing to do with reality at all. It's an entirely politically generated hot air cloud, but it's incredibly important because it does influence their government policies. So it's a really difficult situation where you get this disconnect between reality and the political sphere. But that's what's happened in Australia. I think we've already heard quite a lot about why it's difficult to make credible predictions. Of fisheries productivity in particular, first of all, you've got to have good ocean climate forecasts. Until quite recently, the global models didn't really deal with the oceans in any great detail at all. And even now, they don't include a lot of the coastal and shelf processes, tidal mixing and so on, that are important when you're thinking about biological productivity in fisheries. Just the fact that we don't live in the sea, that you've got to use a microscope in order to see plant life in the sea, that we've got no familiarity, it is actually an important factor in the way that we are able to make credible predictions. We don't control the production systems. On land, farmers control what crop they grow, they control the nutrient supply, they control the water supply. We don't do any of those things in the sea. We do to some extent in aquaculture. We harvest a lot of species with crop forecasts. If you take wheat, rice, maize, a couple of other, that's it, you've dealt with 95% of global crop production. But with fish, in order to get to 95% of global fish production, you'd probably have to include 200 species or something like that. We've got virtually no experimental basis. Most of the projections that are made for agricultural crops are based on experiments. If you want to know what the effect of a 2-degree rise is on a wheat crop, then you can actually put a experimental plot of wheat under those conditions with enhanced CO2 and all the rest of it and see what happens. Even if we could predict primary production, the transfer all the way up the food chain is long and uncertain. So it's not surprising that fisheries predictions or projections are difficult to make. And this is a paper that I wrote recently which deals with a lot of these issues. And it's actually quite critical of the IPCC, because the IPCC says that they have high confidence in the projections of fisheries for the year 2050, 2060, and I think they're mad. I mean, that's actually higher than the confidence that they have in crop predictions, and I don't know how they allowed that through, but they did. And it deals with how we estimate the reliability of our projections. We have to be complete and consistent in how we present that information. The fact is that the fisheries projections are not consistent with the agriculture projections. They're talking about different things. With the fisheries projections, they've actually left out the credibility of all the underlying assumptions. So they're saying if primary production is unchanged, if there is no effect of oxygen, if there is no effect of this, that, and the next thing, then we have high confidence in our projection. Well, everybody all forgets about all those ifs and buts when they look at the confidence statement. So it's whether you internalize all the factors or not, and you really do have to. You have to present all of the factors in a complete and consistent way, I think. And that paper, by the way, it came out in a new Springer journal quite recently, Current Climate Change Reports, and they made it free, so you can download it for free. So, summing up, climate is already affecting marine ecosystems. Fisheries have always been affected by climate. It affects productivity via recruitment, growth, mortality and distribution. It can increase as well as decrease fish productivity. In fact, the IPCC projection, which is a pretty good, well-based projection, maybe not with high confidence, but medium or low, is that in the Nordic seas, particularly the Norwegian Sea around Iceland, there will be quite big different increases in fish productivity over the coming 50 years or so. The reason for that is mainly to do with the effect of temperature on stratification, that because you'll get increased stratification, the nutrient supply will remain in the photic zone, and that will enhance production. In the tropics, the increased stratification will reduce the vertical mixing, and therefore you'll get reduced productivity, primary productivity, and therefore fisheries productivity. So that's a reasonably well-based projection. In spite of the complexity of understanding and managing, we can propose some robust win-win strategies. There's no question that for most stocks in the world, we are still overfishing them. We're just putting too much fishing pressure on them. Reducing that will be a win-win strategy. It'll help both with fisheries production and with dealing with the impacts of climate change. And I think that the signs are that globally fishing pressure is coming down. So we may just be in time to avert the worst for both fisheries and, let's hope, climate. But it's a close run thing. So thank you very much.